Hello everyone, good morning. Thanks for warm welcome. So my research initially started off with looking at the impact of wind generation on frequency stability. I'm going to briefly go over an overview of those impacts and then sort of look towards a solution to those sort of things. So I'll start off with a background to my presentation. How is frequency controlled in the power system? And then from there, I'll look at impacts of wind generation. And then lastly, I will present my new method of optimization for instantaneous reserves. So the frequency on the power system is dependent on the balance between generation and demand. That's because the frequency is directly coupled to the speed of synchronous machines, and those synchronous machines change speed depending on how much mechanical power is supplied through the turbine and then how much electrical power is drawn by the generator. So if we have higher generation than demand, we will expect the seesaw to tip and our frequency to increase. However, the events that are most important to managing frequency occur because of loss of generation or a loss of a pole on the HVDC link. So for these events, the frequency quickly declines as generation is much less than demand, and we have to try and keep the frequency above 48 Hertz. And this is because we need to avoid the all-falls levels that occur at 47.8 and 47.5. These are last-ditch tools to keep the frequency above the 47 Hertz limit. Otherwise, the system cascades and you get a blackout. Before we reach the 48 Hertz limit, we have a series of responses. By 49.5 Hertz, most hydro and thermal responses will be working by now, and at 49.2, interruptible load will start to trigger. Moving on to the impacts of wind generation on reserve requirements. There are two main impacts. The first is to do with the technology that wind turbines use. The rotor speed of a wind turbine is decoupled from the frequency of the power system. And because of that, that inertia that the wind turbine has is not useful for the system operator. So when you get a loss of generation, the frequency will decline more quickly. The second impact is the variability in the power output of wind generation. This will require more balancing and also changes the profile of generation on the power system. So to model these impacts, we have done a study on the New Zealand power system, looking at how the generation profile will change. We have looked at data from 2013 to 2015, creating like a redispatch where we change the profile of generation every 30 minutes. And then from those results, we can record which generation is running, sum up the total inertia, and then record the minimum inertia that we can get on the power system. So in this plot here, I have shown the inertia for a series of scenarios. The minimum inertia is defined as over that year of 2013, particularly for this graph, what is the bottom 1 percentile that the inertia reaches. So for our current situation on the far left, we reach about 12,000 megawatts seconds in the North Island and roughly just about 6,000 megawatt seconds in the South Island. As we increase that wind penetration up to about 2,000 megawatts, our inertia reduction plateaus, and that's because of our hydro resources and geothermal resources that we have. They are not likely to turn off. So we've looked at inertia. Now we want to look at how does our contingencies change in size. And one that's been found to be the most dominant is the the transfer of power between the South Island and the North Island. This will create a risk of losing one of those HVDC poles onto the North Island system. To see those results, I've shown here a duration curve for that risk. So on the y-axis, we have the size of the contingency, and then on the x-axis, we have the portion of time that that risk is above that given value. So if we look at the 1000 megawatt case, that's the yellow line, we can see for about 20% of the time that our risk is above zero, but for the remaining 80% of the time, there is no risk at all. So with each scenario, from base up to 4000, we see that the curve extends further right, therefore our contingency size increases in general. So what does this all mean for instantaneous reserves? So it will mean a greater peak demand for FIR. And to see why this is the case, I will go through sort of the reasoning behind it. So we'll consider two situations, a high inertia situation and a low inertia situation. Starting with the high inertia, I've shown here on the left a time plot of frequency, and then on the right, the required reserve response to get that frequency transient. So for a high inertia case, we expect the frequency to drop more slowly, and then we get our minimum frequency at 6 seconds. And that 6 seconds is where fast instantaneous reserves is defined. So by 6 seconds, we need 400 megawatts of reserve to replace 400 megawatts of generation lost for that contingency. Now moving to the lower inertia situation, the frequency drops more quickly, and we need to have the reserve respond more quickly as well, and our minimum frequency is reached by 4 seconds. To guarantee that reserve response of 400 megawatts by 4 seconds, we need 670 megawatts by 6 seconds. Now, this additional reserve is not necessarily used, but it is required to guarantee that response rate by 4 seconds. So an overview of what I've just said, we should expect periods of low inertia and high risk under high penetrations of wind generation. This will result in quickly declining frequency during contingencies. This requires more fast instantaneous reserve to guarantee that response rate, and therefore generation and reserve capacity will be more constrained in the North Island as a result. The final part, the final third, I'm going to present on the solution to this problem. So what I propose is to include the response speed of reserves into the SBD market optimization that Transpower does for the electricity market. So we have two responses. The first is an instantaneous response, where we have a delay after the time of the contingency, and then we optimize the final power output of that reserve provided. In the current formulation, what is optimized is just the final output. There is no time delay in those simulations on that optimization. The second response is a ramped response, and this is to model the more typical types of reserve from hydro and thermal generation. This has a constant ramp rate, and also the final output is adjusted for the optimization. From those reserve responses, we determine the frequency transient by this differential equation. The sensitivity of this equation is determined by the inertia, given by the H symbol there. From that frequency transient, we put constraints on the frequency. So that dark solid line at the bottom is a stepped frequency limit. Each time you have a step in that frequency limit, you have a constraint in the equations. And then at the time at which you reach the minimum of the frequency, you also have a constraint as well. To show this for an example, I have got a set of interruptible load offers and a set of spinning reserve offers. They each have their own time delay, their own price, and their own quantity. And then with the spinning reserve, there's an additional ramp rate. Generally, if you look at the prices, they go up in price as short that delay is. So I've developed this optimization tool. The results shown in this plot are the given frequency transients for different inertia values. So depending on what the inertia is, you get a different frequency transient, and then the ones shown here in this plot are the optimal results. Again, we got a frequency limit, which is initially at 48 Hertz, and then after a certain amount of time, there's a series of step responses, and this is to ensure that the frequency returns back to its nominal value. So you can see for small inertia situations, the frequency drops very quickly and therefore requires a fast response from all the reserve providers, whereas when the inertia is very high for this optimization, it is the later frequency limits that become the binding constraints. This form of optimization will mean changes to SPD. Currently, SPD solves a mixed integer linear programming problem. To have this optimization within it, we would need to move to a quadratically constrained programming problem. This is an increase in complexity. However, the convexity of the solution space is still convex, so we should still expect practical solve times. So in conclusion, I have developed a new optimization approach that has been formulated for fast instantaneous reserve. This avoids the unnecessary over-procurement of FIR during low inertia and high-risk conditions. And also, since we include those response speeds from those reserve providers, therefore, in this optimization, we are valuing those response speeds in that optimization. And thank you to our supporters.